Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is fourth lecture of numerical analysis, and the topic of today's lecture is the Hermite interpolation. Just like previous methods, Lagrange polynomial, divided differences, centered differences, where we can approximate data by a polynomial and can study the curve which we are getting, and then we can do the interpolation. Exactly in a similar fashion, this technique is also working. The difference between the previous techniques and this technique is that the degree of polynomial is higher than the degree of polynomials which we were getting in previous methods. First of all, let's go for what is Hermite polynomial. Let's assume we are having an interval and function f is along with its derivative is continuous in that interval. Let's do the partition of this interval such that a is equal to x naught, less than x1, less than xn is equal to b is usual. Hermite polynomial is a polynomial of least degree such that it satisfies the following two properties. This is the first property and this is the second property. Remember, this p is the polynomial and we are approximating this function by that polynomial. This condition means that value of the polynomial at x is equal to x0, x1, x2 up to xn coincides with the value of the function at x0, x1, x2 up to xn. In other words, p at x0 is equal to f at x0, p at x1 is equal to f at x1, and so on. P at xn is equal to f at xn. This is the condition which hold in the previous methods also. But this is the second condition. Derivative of the polynomial at x0 is equal to derivative of the function at x0. Derivative of the polynomial at x1 coincide with the derivative of the function at x1, and so on. Finally, derivative of the polynomial at xn coincide with the derivative of the function at xn. If these two conditions are satisfied, then we say that the polynomial p is Hermite polynomial. This is the definition of the Hermite polynomial. Two different ways to find out the polynomials. One way is to use a theorem. Of course, this theorem I have taken from the Burden and Fair book, Numerical Analysis. The statement of the theorem is, if the function along with its derivative is continuous on this interval, and x0, x1, x2 up to xn are distinct points in this interval, then the unique polynomial of least degree, which coincide with the function f and f its derivative at the data points, is the Hermite polynomial, and its degree is 2n plus 1, and the polynomial is given by this expression. You can see in this case that there are n plus 1 number of data points, and the degree of polynomial is 2n plus 1, which is different from the degree of the previous polynomials, because according to the previous methods we can get polynomial of degree n only, but in case of Hermite we can find out polynomial of degree 2n plus 1. F xi's, these are given points. F prime of xi's, these will be given points. In previous methods you saw that the derivative of the function was not given to us, but in this case we need derivative of the function at the data points h and I and h hat and I. These are the polynomials given by. This is the polynomial. You can see this term has been multiplied with lni square of x, and this is the expression for h hat. What is L? L and I, these are Lagrange coefficients which you are using in Lagrange polynomials, and L and I prime, these are the derivatives of the Lagrange coefficients. Here also we are just using Lagrange coefficients. So L and I of x, these are Lagrange coefficients. Further, if the function along with its derivatives up to 2n plus 2, this is continuous, then the function can be approximated by a polynomial plus the error term. This is the error term when you are approximating function by the polynomial. xi is usual, it lies between x0 and xn, or it lies between a and b. We don't know explicit relation for xi, which you already know. This is a kind of critical point when you are approximating maximum value of this function, absolutely maximum value of this function, and this can be used for computation of the upper bound of the error when you are approximating value of a function at a particular point. Let us consider an example. The target is to use the theorem which we stated right now and approximate this data by a polynomial. So you can see in this case, this is x0, x1 and x2. The value of n is equal to 2. The value of n is equal to 2. So when the value of n is equal to 2, so 2 into 2 plus 1, 5. We can find out polynomial of degree 5 for this data. And if you remember, using the previous techniques, we can find out polynomial of degree 2 only, the highest polynomial. And in this case, we can find out polynomial of degree 5. So let's if you substitute n is equal to 2 in this expression, so you are getting this formula gives you this value. The value of n is equal to 2. Now let's do the expansion. When I is equal to 0, I is equal to 1 and I is equal to 2. I is equal to 0, f of x naught, h2 naught of x. I is equal to 1, f of x1, h2 1 of x. I is equal to 2 f of x2 h2 2 of x. So this is the expansion of the first summation. Let's come to the second summation. I is equal to 0 f prime of x naught h2 naught height of x. This is the term. When I is equal to 1 f prime at x1 h2 1 height of x. When I is equal to 2 f prime at x2 h2 2 height of x. So this is the expansion of the second summation. You can see in this case f of x naught, f of x1, f of x2. These are the values coming from the table, the first column. F of x naught, f of x1, f of x2. F prime of x naught, f prime of x1, f prime of x2. It's coming from this column. F prime of x naught, f prime of x1, f prime of x2. These quantities are known. We have to find out h2i of x and h2i height of x. You know that this is the formula. This is coming from the theorem. When we substitute n is equal to 2, so the first expression gives you this value. And when n is equal to 2, so the second expression gives you this value, where the value of I is starting from 0, 1, 2. It depends upon the number of points which you have. Again, if you look at this formula, f2i, these are Lagrange coefficients, and L2i prime, these are the derivatives of these coefficients. So let us find out the missing values. These x0, x1, x2 coming from the data. Lagrange polynomials. You know that the property of the Lagrange polynomials, Lagrange coefficients was, if this I is equal to this j, we should get 1, and when this I is not equal to j, we should get 0. This is the condition which you already did in Lagrange polynomials. And if I use this property, so this is expression for ln I of x. You can see here, when I replace this notation is using for multiplication. It means that x minus x naught divided by x I minus x naught multiply by x minus x1 divided by x I minus x1, and this will continue until we reach up to n. So x minus x I minus 1 divided by xi minus xi minus 1 into x minus xi plus 1 divided by xi minus xi plus 1, and it will reach up to x minus xn divided by xi minus xn. And you can see that when I replace x by xi, so all these factors will cancel out and you are getting 1. And when it's different from, for example, x is equal to x naught, so this one of the term will become 0, x is equal to x1, one of the term will be equal to 0, x is equal to xi is not there, so that's the reason I can't fit that. X minus xi is not there in numerator. Similarly, xi minus xi is not there in the denominator, otherwise this denominator will become infinity. So this satisfies these two conditions. Let's use this definition to find out the Lagrange coefficients. When already we know that n is equal to 2, when I is equal to 0, when I is equal to 0, so it means that your numerator will be x minus x1 into x minus x2. Yeah, x minus 0.2 and x minus 0.3 divided by, replace this x by x naught. x naught is 0.1. So 0.1 minus 0.2, 0.1 minus 0.3, and if you simplify this one, you are getting a polynomial of degree 2. You are getting polynomial of degree 2 given by this expression. When I is equal to 1, so this is the Lagrange coefficient corresponding to x is equal to x1. So x1 is missing in numerator, x1 is 0.2. So x minus the rest of the points, x minus x naught, x minus x2 divided by, replace x by x1. So x1 is 0.2, 0.2 minus 0.1, 0.2 minus 0.3. And if you simplify this one, you are getting this polynomial. And now when I is equal to 2 in this case, we are getting L2, 2. So you can see that this corresponds to x is equal to x2. So you can see that x2 is missing in numerator. X minus x naught, x minus x1 divided by, replace x by x2. x2 is 0.3. 0.3 minus 0.1, 0.3 minus 0.2, and if you simplify this one, you are getting polynomial of degree 2. So we computed the Lagrange coefficients which we need in the construction of Hermite interpolation. Next, we need their derivatives. So L2 naught of x, differentiate this function with respect to x. So you are getting 100x minus 25, which is given by this expression. Differentiate L2 1 with respect to x, you are getting minus 200x plus 40, which is there. Differentiate L2 2 of x with respect to x, you are getting 100x minus 15, and that is given by the last expression. Now, let's find out the values of these derivatives at the data points. For this purpose, let's find out values of this coefficient at the data points. Replace x by x naught, which is 0.1. We are getting minus 50. Replace x by x1, which is 0.2. We are getting minus 5. Replace x by x2, which is 0.3. We are getting 5. Now let's come to L2 1 prime. Replace this x by x naught, which is 0.1, we are getting 20. Replace x by x1, which is 0.2, we are getting 0. Replace x by x2, which is 0.3, we are getting from this expression minus 20. Come to the last one. Replace x by x naught, which is 0.1, we are getting minus 5. Replace x by x1, which is 0.2, we are getting 5. Replace this x by x2, which is 0.3, we are getting 15. So you can see that we calculated all these derivatives at all data points. So why? Because we need them in the construction of the polynomial. Now let's come to h and i's. You know that the value of n in this case is 2, and the value of I is starting from 0 and reaches up to 2. So we have to find out h2 naught, h2 1 and h2 2. When I is equal to 0, h2 0 is equal to 1 minus 2 into x minus x 0. X naught is 0.1. So you can see it's written over there. Similarly, L2 naught prime 8 x naught. X naught is 0.1. And L2 naught at x square, which is there. Now if you look at this expression, L2 naught of x is given by 50 x square minus 25 x plus 3. L2 naught prime at 0.1 is given by minus 50. So substitute these values, we will get the polynomial of degree 5, and that's given by this relation. Now when I is equal to 1, so h2 1 of x is given by this relation 2, 1, and x1 is 0.2. This will be 2, 1 prime at x is equal to 0.2. This is L2 1 square at x. So we have computed this value in the previous slide. Remember, this whole term has been multiplied with L2 1 of x square. So if you substitute the values, you are getting polynomial of degree 4. So h2 1 of x is the polynomial of degree 4, which is given by this relation. Let's find out L2 2, the value of xi is x2. I is equal to 2. X minus x2 is 0.3. This will be 2 at 0.3. And this will be L2 2 square of x. We know these values. This polynomial we know from the previous slide. This value is known in the previous slide. And if we substitute these values, we are getting polynomial of degree 5. And that polynomial is given by this relation. So remember, substitute these values and simplify. So you are getting the polynomial of degree 5. We computed the values of h and I. Now let's come to the heads. H and I head is given by this relation. The value of I, the n is equal to 2, I is equal to 0, 1, 2. We have to find out h2 not head, h2 1 head, and h2 2 head. These are the values we have to find out. When I is equal to 0, so this is x minus x naught, x minus x naught is 0.1, which is there. And this will be L2 naught square of x. And also you know that we have computed this value already. So let's substitute the value and we are getting a polynomial of degree 5. Remember, it's clear from here. This will be we have to square that and then multiply by x. So this is the polynomial you are getting. Now let's substitute I is equal to 1 in this expression. So we are getting h2 1 heat, x minus x1, the value of x1 is 0.2, multiply by 2 1 square, and again this value is known to us. So let's substitute the value, and when we substitute the value, we are getting a polynomial of degree 5 here also. When I is equal to 2, so h2 2 head is given by x minus x2, the value of x2 was 0.3, and L2 2 square. This value is known, we have computed already there, and when we substitute that value over here, we are getting a polynomial of degree 5, and that's given by this relation. Now you can see f of xi's are known from the table. F prime at xi's are known from the table. We computed h2i's and which we computed h2i's head. So all the required values in the formula, they are known now. I reproduce the table, putting all the values which we computed in equation number 1. What is equation number A? What is equation number A? Equation of number A is given by this relation. Now, n is equal to 2, polynomial of degree 5. F of x naught is this value, f of x1 is this value, f of x2 is this value, f prime of x0 is this value, f prime at x1 is this value, and f prime at x2 is this value. And h2 naught, h21, h22, h2 naught prime, h21 prime, and h22 prime ahead. We computed these values. So let's find out the required polynomial, h5 of x. F of x naught. F of x naught is given by minus 0.29004999583, which is written over there. h2 naught is given by this polynomial. Second term, f of x1. So f of x1 is coming from here. You can see that this is the number. And h21. This is the polynomial which we computed already. And if I come to this one, f of x2 is minus 0.18140197716. That is the value over here, you can see. And multiply by h22. So this is the value of h22. That's the polynomial of degree 5. Now let's come to the second summation. F prime of x naught. Prime of x naught is given by this value, and this value is given over here, written over here, minus 2.899017501. Multiply by this is the value of h2 naught height plus f prime of x1. F prime of x1 is minus 2.61592012142, which is this value. Multiply by this is the value of h21 height. This is the value of the polynomial h21 height. And when I go for this term, h prime at x2 is given by this value. And you can see that this is the value which we need. Multiply by h22 height. So this is the polynomial of h22 height. Now you can see that if you simplify this, you are getting a polynomial of degree 5. But remember, you need the multiplication. These are the coefficient of x raised to the power 5. But remember, there are some factors in multiplication also. X raised to the power 4, x raised to the power 3, x square, and x, and then you're having the constant terms. And if you simplify this one, you are getting a polynomial of degree 5, and this is the polynomial of degree 5. You can see in this case, we replace the data by a polynomial. How many data points we have? We are having 3 data points. So if you are using the techniques which we discussed before, then highest possible polynomial, degree of polynomial of highest degree possible will be polynomial of degree 2. But you can see in case of Hermite polynomial, we got a polynomial of degree 5. And you know that when we are increasing degree of the polynomial, we are expecting small error and we are expecting better accuracy. And this method says that we are increasing degree of the polynomial. In other words, they are saying that we are computing higher degree polynomial. So in other words, we will have better accuracy. But remember, the problem here will be that you need the derivatives of the function also. We need the derivative of the function also at the data points. Whereas these values are not required and the techniques which we did before. So when you have some experimental data, for example, you perform an experiment and you want to study different behaviors. If you are looking for the area under the curve, so of course the area under the curve, if curve is not known, so how you can find out area in that case? You need the integration. But now this technique helps you that you computed the polynomial, you replace the data by the polynomial of degree 5. Now you can find out the derivatives if you want to study the changes. You can find out the derivatives. It's straightforward because this is a polynomial, and study of the polynomial, derivative of the polynomial is straightforward. It's very easy. So if you want to study nature of the problem, for example, you are looking for the critical points, where the critical points will be. So now this is a simple equation. You can find out the derivative, you can find out the critical points, you can find out the maximum and minimum value of the function. You can talk about the tangent lines. You can talk about the gradients. You can talk about the curvatures. These are different things you can study with the help of the derivative of the function. Now you can see you have just data points, and you can study different features of your data. Similarly, if you do the integration, for example, if you integrate this function between 0.1 and 0.3, then you can study the area, you can find out area of the region bounded by your data points. You can find out area of the region bounded by the data points. And similarly, if you need some other applications, which are the applications of the integration, so this can help you. This was one case, but now if you want to do the interpolation, for example, you want to find out the value of the function at the point which lies between 0.1 x is equal to 0.1 and 0.3. And that point is not available here, but your experiment is such that you need that particular value. What is the behavior of your data at a particular point? So again, like the previous methods, the Hermite polynomial can also help you. Just replace x by that particular value and you can find out value of the function at that particular point. But remember, that will be an approximated value. For example, if my interest lies to find out the value of the function at x is equal to 0.18, then just replace x by 0.18 and you are getting this approximated value of the function at 0.18. And so you can see that 0.18 is not available there. But that was the requirement of your data. Your interest lies in the value of the function at x is equal to 0.18. And similarly, you can find out the value of the approximated value of the function in any point lying in this domain. So this is the way how the Hermite Hermite polynomial will be working. I think this will clarify that how you can use the theorem to find out the polynomial of degree 5. Of course, the question is lengthy. There are a lot of calculations over there, but remember, whenever you are doing the calculations, you have to be very careful in your computations, because if the calculation is lengthy and if you do the mistake at a single point, then it will destroy the final result. But remember, if you are working on any project, then you have to be careful about the project, because you got the project and the project need careful study. So replace the data by polynomial, do the interpolation, study the nature of the curve, look for maximum, minimum, tangent lines, points of inflection, concavity. So you can find out from here. Similarly, you can find out the area for your data also. And I think the things will be clear. Again, I'm telling you, in case of any problem, please send me the email. I will try my best to reply to you and resolve your problems. If you keep quiet, so I'm repeating my words again, that either you know each and everything or you know nothing. But the second choice, I don't agree with that, because you know a lot. But whenever you are facing the problem, so let's resolve the problem. Thank you very much.